Hello, welcome to the Henstitute. Today we are going to be talking about fluid dynamics, specifically Bernoulli's equation. So Daniel Bernoulli kind of gets credit for a lot of stuff with fluid dynamics. And one of the things I want to highlight after we get done with our notes and we've done some problems, that not everything actually is explained with Bernoulli's equation. Instead, some of them actually have the concept of the Magnus effect or the Coanda effect, which should pop in. So we'll see some of that later. Before we get into the Bernoulli equation, though, we need to kind of talk about a couple of things dealing with fluids. First off, fluids are going to accelerate as they go toward a lower pressure region. So looking at A here, we know from the equation of continuity, if I have a wide pipe that then narrows down, that the fluid is actually going to go faster in the narrow section than the larger section because of the volume flow rate has to stay constant. So if I'm looking at this is a larger area, cross-sectional area 2. This is a smaller cross-sectional area, so it's actually going to go faster. So it's accelerating to the right. Well, the other part that does, and we're going to find out why with Bernoulli's equation, this causes a change in pressure. If you are actually moving faster, we saw this with the fluid simulation lab, you actually have lower pressure. And so this fits with what we know about fluids flowing from high pressure to low pressure situations. The other one we want to bring into account is if I have fluids flowing through a pipe, but the diameter stays exactly the same and therefore the speed stays the same, the change in height is still going to be important. It doesn't actually, they don't have to be right above each other like we dealt with fluid statics. They could be sideways and they could be moving. So we're still going to have the pressure being lower at higher levels, even though we may not have a change in the area of the pipe. So I'm going to be looking at a situation where I have some fluid at point 2 and point 1, and it's going to flow through here, and it's going to be changing its height. So we've got it labeled as Y2 and Y1. I often just call them H1 and H2 over here. The book likes Y instead of H. And we're going to have different pressure sensors on here. We're going to have different velocities. So we're looking at two different points or different points along this fluid. Before I can get into Bernoulli's equation, really Bernoulli's equation pretty much boils down to energy conservation. So what we mean by that is we have to go back to chapter 6 from last year in AP Physics 2, which during my classes was when we were actually, we were off. We were remote learning by that point because we do that in March. There are two major things that are going to be important, but the main idea of energy conservation is the work that you do to some system, to some object, is going to cause a change in energy. And it can cause a change in kinetic energy. It can cause a change in gravitational potential energy. It can also cause a change in elastic potential energy, but I'm not going to put that on here because with our incompressible fluids, that doesn't matter. Now, you may not remember what work was, but work was actually the product of your force acting on an object, actually the net force acting on an object, and the displacement of the object. So this is the way I wrote it. I talked about lifting objects, moving objects, and that type of idea. Kinetic energy itself is 1/2 mv squared, where v is the speed of it. So that's why it's kinetic energy. It deals with speed. We're going to maybe see this pop up as a 1/2 rho v, because that's how we'll find it, times a little v squared. And that's going to be kind of suck because we're going to have to deal with that particular concept. How do I deal with that volume? But you'll see in a little bit. And then gravitational potential energy dealt with finding how much energy there was due to gravity at a particular position. And so gravitational potential energy was the mass of an object times gravity times height from some reference point. Again, we're going to be dealing with fluid, so the density of the fluid times volume times gravity times the height is going to be important. So where does that fall for what we're trying to do? change our color here. So what that means for us is that work is going to be our net force times a displacement. Now they're using S to represent displacement. And they're going to talk about like a little fluid moving a certain distance in that particular pipe. So they're basically taking this little section of pipe. And so if I rearrange that, that would be caused by a difference in force. So if I have a slight difference in height or a slight difference in speed, then we're going to have a force acting on one side and a different force acting on the other. And the difference between them is going to be important. And it's happening because we have a slightly different pressure. So remember that F equals paw. But if we were talking about a difference in force, it's caused, or a net force, it's caused by a difference in pressure. So that's where this delta P A is going to come in, and then it's multiplied by S. But wait a second, A times S, wouldn't that be the cross-sectional area times the height of this? So if I think of this as maybe a cylinder, that's just the volume of the cylinder. So this part, this A times S, is just the volume of the cylinder, or it could be rectangular, it doesn't have to be circular. And then our delta P is just P2 minus P1. So we have a brand new way of finding work. The other parts that we have is this is another way of writing the idea of changes in energy. I wrote it slightly different. So I wrote it as delta KE plus a delta GPE. But your change in kinetic energy is going to be the kinetic energy at one moment in time minus the kinetic energy at another. So there's your delta KE. And then they like to use Y's instead of H's, but they've got potential energy at one point minus the potential energy at another point. Now, why are you using 1 minus 2? And the reason why they're doing that is because if I have a fluid flowing through something, you're always going to be going from high pressure to low pressure. So we want our P2 minus P1. We want P2 to be larger than P1. And what we typically do is we treat P2 as the lowest point and P1 as the highest point. That's what we've been doing. So we're actually going from P2 to P1, and the difference in that is always going to be final minus initial. So we're finishing up here at P1 where it's lower pressure and starting at P2 where it's actually higher pressure. So it's kind of weird when we do that. So that's why it's the 1 minus 2 instead of the other way around. Now up here, my delta P is still going to be P2 minus P1 because P2 is going to be larger. So now what we're going to do is we are going to take this and we're going to substitute that in. So we're going to put in P2 minus P1 times velocity or times volume, sorry. That's going to be my work being done. Now, this has a whole bunch of masses. And like I was showing before, technically I know mass is equal to density times volume. Well, here's the cool part. There's volume. So if I divide these volumes over, and I divide every mass by a volume, what you will find is all those can be replaced by densities. So here's a density, 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 and I don't have to worry about it. And what we end up with, if I bring all of the P2s together and all of the P1s together, the P or the 2s together, and I put all the 1s together, since I was subtracting all the 2s here, I can bring them over to the other side, they'll be positive. I can take this pressure and bring it over to the other side, and it's going to be positive. So in essence, Bernoulli's equation says that you have three different things that have to stay constant. The pressure of the fluid plus the kinetic energy per unit volume of the fluid plus the potential energy per unit volume of the fluid stays constant. So this is a constant value. It doesn't matter what's happening to that fluid. Now this is only going to work for non-viscous incompressible fluids, ideal fluids. So if they compress or they have friction, we don't worry about it. But for us, this is the way we're going to write it. Now, sometimes you'll see me, instead of Y's, I like to use H's here. So I often will write H1 and H2. If you want to keep it as Y's, I don't really care. It'll work either way. So let's try out some ideas. When the truck is stationary, the tarp on the top lays flat, but it bulges outward when the truck is speeding down the highway. What can account for this? Well, if you come back for this idea, let's assume that the heights are not changing. So the heights are basically the same, but I do have a difference in speed. At one time, we had here, we have a speed that's equal to 0, but here I actually have a speed flowing over this. So I have a different one that's not equal to 0. So it's going to be something greater than 0. Well, one of the things you're going to find for Bernoulli's equation is if I have pressure 1 plus this 1/2 rho V1 squared equal pressure 2 plus this 1/2 rho V2 squared, that, assuming the densities are the same, which is it's air, it's the same fluid, if this speed is greater than this one, what you're going to have to find is that this pressure has to be lower. So when you have moving fluids, you actually have a lower pressure. P2 here is going to be less than P1, which would be up here. This is very important. We're going to see this pop up a lot, that moving fluids produce lower pressure because they're moving. The faster they're moving, the more they do that. We often think of this with wings. The air flowing over the top is faster than the air flowing on the bottom, and therefore you have less pressure. So you have a pressure difference. I'm going to show you a video later where this is not the only thing to think about with a wing, but it is one aspect that helps. And so we kind of get that situation. Another application is if you have fluid flowing through your sewer line, we often put a little water-filled trap here in your sink. So if you've never noticed, they've actually kind of bulge out. Well, if this starts moving, it's actually going to produce lower fluid, and this would actually, it would suck this out, and you would have that gone, and then you'd smell the sewer gas. So what we often do is have a vent to the outside so that we have the same pressure here as we have here. It keeps the pressures the same, and that can kind of keep that from having that fluid, that sewer gas coming up. Baseballs, throwing a curveball. One way of describing it is with Bernoulli's equation. So if I actually throw the baseball and get it spinning in a particular direction, so let's say it's causing this particular spin, what it's going to do is the ball, and the reason why you have the threading on the ball itself, it's going to actually grab some of the air, and due to friction, it's going to speed up the air here. So you have faster air here. It's moving in the opposite direction, so you get slower air. This is actually going to cause a difference in pressure, and then a difference in pressure is going to cause a net force on that ball. Now, this is misleading because there's actually other aspects that are going to this. We'll talk about the Magnus effect a little bit later, as well as a thing called the Coanda effect. So just kind of keep that in mind for right now. Here's another cool part is, let's say you have a tank that actually has fluid flowing out here, and you want to find an expression for finding how fast it's going. So you have to pick a couple of points on here. One of them would be the top of the fluid. Another one would be where the fluid's coming out. And so if I have fluid flowing down and out of here, what I know is my P2 plus 1/2 rho times V2 squared plus rho G, call it like H2 equals all this. So this is Bernoulli's equation. Up here, we kind of think of this as moving extremely slow. So V2 is approximately equal to 0. So if it's a big enough tank, it doesn't drop real fast compared to the fluid coming out. So V2 is pretty close to 0. We wipe it out. We also need some point to measure things from. So if we have water coming out at a certain place and we have the top of the fluid here, like if you were to take this tube and actually turn it, you would actually find the water would go up to the same height. So it would stay at the same height as it drops. That's just the way it's going to work. We're going to find, because it has to try to keep that conservation of energy. But here, if I measure some height, what I can kind of think of is I can kind of think of y1 as being 0, and it's really just y2 that's important. So I basically get rid of this h1, and I have that kind of disappearing. Up here, I have air pressure. So P2 is just air pressure. Well, if this is exposed to the air, what you're going to actually find is this thing is flowing out, but you also have air pressure pushing on it. So P1 is also air pressure. So since both of these are air pressure, they disappear, and you just end up with these two parts to it. Well, here's a couple of things that are neat. Look, bye-bye densities. And if I rearrange this, multiply by 2, I find out that the speed of this object, or this fluid coming out, is just 2g times h2. That's a great concept. What it means is it's almost like as fast as a falling object. If you just drop something from that height and it fell that height, it would be moving that fast. If you have fluid flowing out, assuming you don't have any friction, so it's a non-viscous fluid, it would flow out at that same speed. It's just kind of amazing the stuff you can do with Bernoulli. And they kind of lead you through this same idea and come up with the same equation down here. That pretty much finishes it up. I do want to do some sample problems with this. So I'm going to eventually assign some problems, but we're going to also be kind of looking at some examples because I didn't do many examples in this. I hope you enjoyed this edition of the Henstitute.